So. I'm just gonna read this book, bruh. I'm not really like. I just want to get cozy and read. Any function naturally to be regarded as computable is computable by a Turing machine. Okay, so you have some model of computation. Yeah. Extended church Turing thesis that any function naturally to be regarded as efficiently computable is efficiently computable by a Turing machine. Hold on. This book is like this book is crazy, man. Yeah. Great. I propose to answer the question: can machines think? This should begin with definitions of the meaning of the terms machine and think. The definitions might be framed so as to reflect, so far as possible, the normal use of the words. But this attitude is dangerous if the meaning of the words machine and think are found by examining how they are commonly used. It is difficult to escape the conclusion that the meaning in the answer to the question, can machines think, is to be sought in a statistical survey such as a Gallup poll. But this is absurd. Instead of attempting such I'll replace the question by another which is closely related and expressed in relatively unambiguous words. The new form of the problem can be described in terms of a game in which we call the imitation game. It is played with three people: a man, a woman, and an interrogator, who may be okay. The interrogator stays in a room apart front the other two. What? I think this is supposed to be from. I think that this is a problem of OCR. The object of the game is for the interrogator to determine which of the other two is the... Okay, the interrogator is allowed to put questions to A and B thus. C. Will X please tell me the length of his or her hair? Now suppose X is actually A. Then A must answer. It is A's object in the game to try and cause C to make the wrong identification. Now we ask the question, what will happen when a machine takes the part of A in this game? Oh, for fuck's sake, this thing is so stupid. Okay, so in this game, let's say I'm the man, and I'm trying to make him guess wrong. Wait, hold on, let me read the problem again. Alright, so it's the man's objective. So, I would just, every time I would just respond, I'm the woman. then the woman would always respond, I'm the woman. So it should be totally indistinguishable. Uh, right, okay, that checks out. What will happen when a machine takes the part of A in this game? Wow, that's interesting that this is the game. Okay. As well as asking what is the answer to this new form of the question, one may ask, is this new question a worthy one to investigate? The latter question we investigate without further ado. Okay, I don't know. I don't even know what that means. The new problem has the advantage of drawing a fairly sharp line between the physical and intellectual capacities of man. No engineer or chemist claims to be able to produce a material which is indistinguishable from the human skin. It is possible that at some time this might be done, but even supposing this invention available, we should feel that there was little point in trying to make a thinking machine more human by dressing it up in such artificial flesh. This is so weird. The form in which we have set the problem reflects this fact in the condition which prevents the interrogator from seeing or touching the other competitors or hearing their voices. Some other advantages of the prose criterion may be shown up by specimen questions and answers. Thus, please write me a sonnet on the subject of the fourth bridge. Count me out on this one. I could never write poetry. Add this. Do you play chess? Yes. Okay. Oh. The question and answer method seems to be suitable for introducing. Why am I blanking on what that's called? Oh, never mind. The question and answer method seems to be suitable for introducing almost anyone. Oh, okay. The game may perhaps be criticized on the ground that the odds are weighted too heavily against the machine. If the man were to try and pretend to be the machine, he would clearly make a very poor showing. He would be given away at once by slowness and inaccuracy in arithmetic. May not machines carry out something which ought to be described as thinking, but which it may not machines carry out something which ought to be described as thinking, but which is very different from what a man does? This objection is a very strong one, but at least we can say that if nevertheless a machine can be constructed to play the imitation game satisfactorily, we need not be troubled by this objection. It might be urged that when playing the imitation game, the best strategy for the machine may possibly be something other than imitation of the behavior of man. This may be, but I think it is unlikely that there is I think it unlikely there's any great effect of this kind. In any case, there's no intention to investigate here the theory of the game, and it will be assumed that the best strategy is to provide answers that would naturally be given by a man. Oh, okay. Okay. It's kind of an interesting assumption. It is natural that we wish to permit every kind of engineering technique to be used in our machines. Every kind of engineering technique to be used in our machines. We also wish to allow the possibility that an engineer or team of engineers may construct a machine which works but whose manner of operation cannot satisfactorily be described by its constructors because they have applied a method which is largely experimental. I honestly don't really quite get that. Finally, we wish to exclude from these machines men born in the usual manner. It is difficult to frame the definition so as to satisfy these three conditions. One might, for instance, insist that the team of engineers should all be of one sex, but this would not really be satisfactory, for it is probably possible to rear a complete individual from a single cell. But we would not be inclined to regard it as a case of constructing a thinking machine. This prompts us to abandon the requirement that every kind of technique should be we are the more ready to do so in view of the kind that the present interest in thinking machines has been aroused by a particular kind of machine, usually called an electronic or digital computer. So that's interesting. Following the suggestion, we only permit digital. I mean, that's the whole thing, man. It's like, we're getting so good at biology, we truly can make a thinking machine. I mean, it's amazing that, when was this published? Does it say? In 1950, we were talking about taking a single cell from a man and raising it to a full human capable of thinking. It may also be said that this identification of machines with digital computers, like our criterion for thinking, will only be unsatisfactory. It may also be said that this identification of machines with digital computers will only be unsatisfactory if it turns out that digital computers are unable to give a good showing in the game. But whether there are imaginable computers which would do well. Bro, I love the theory of computing. I'm so unknowledgeable about it, but I want to get, I want to know it. And the whole reason why I'm doing this is I feel like I can't understand organic chemistry unless I get a better understanding of quantum mechanics, because it's all about the wave functions and stuff. But so I'm reading this, but it's like, you know, I don't know. It's just like I'm going down the rabbit hole. It's a good rabbit hole, though. Okay. The idea behind digital computers may be explained by saying that these machines are intended to carry out operations. The idea. Okay. The human computer is supposed to be following fixed rules. He has no authority to deviate from them in any detail. We may suppose that these rules are supplied in a book which is altered whenever he is put onto a new job. He also has an unlimited supply of paper on which he does his calculations. He may do his multiplications and additions on a desk machine, but that is not important. If we use the above explanation as a definition, we shall be in danger of circularity of argument. We avoid this by giving an outline of the means by which the desired effect is achieved. A digital computer can usually be regarded as consisting of three parts: store, executive unit, control. The store is a store of information corresponds to the human computer's paper. Whether this is the paper on which he does his calculation or that on which his book of rules is printed. Insofar as the human computer does calculations in his head, yeah, this OCR is a little goofed up. I'm curious if we can find a real PDF of. Alright, let's skim the rest. Actually, wait, I want to go back to the part about um not about this, but about... Yeah, okay. Alright, let's just read... I guess let's just read this. I read this last night, but I didn't really get it. Okay, for me, the thing that's weird about this one is, say you want to enumerate, say you want to enumerate all the Turing machines of a given, size or whatever, and then you want to simulate all of them. Well, if you hit one that, it's like, how do you know how far to move over? Like, let's say it just goes to the left and it just overwrites whatever. Okay. So what is the universal Turing machine? Like, what is it? It takes as input the specification of a Turing machine, right? Let me make sure that I have that right. I'm pretty sure that that is right. Okay, so basically the universal Turing machine is a Turing machine that basically takes as input the specification of a Turing machine and is able to run it. So what? I feel like it's not. I feel like it's probably exists, right? Yeah, I said that wrong. But I mean, like, oh, but see, that's the thing. You could write a program in Python super easily that takes as input a Turing machine and simulates it. But is there a Turing machine? I guess I saw that thing that takes a Python program and turns it into. I think I remember in Scott Aronson's blog he links to a Python, something that compiles Python to a Turing machine, which is pretty sweet. It got kind of nice outside, so I think I might what is like what it okay, more precisely, what is the smallest Turing machine that simulates a Turing machine? Yeah, see, that's exactly what I was thinking. What happens when you look up universal Turing machine? Oh, we already have this open. Wait, but is there an example? Oh, here we go. Oh, wow. So how does it all work though? Wait, is this rule 30? No, it's not. No, it's not. Steven always going after him, bro. That's so funny. Yeah, okay, wait. So, but how, okay, so and then how do they encode it? So let's see here. So, okay, they have this. So yeah, let's look at Minsky's UTM. Okay, we can... Alright, I'm gonna end the stream and go outside, because it's sunny and I just can't stand to be inside. So we will continue with this book. This book is hard, bro. Like, yeah, I want to understand this. Can we prove there's no program to solve the halting problem? His key idea is not even to try to analyze the internal dynamics of such a program, supposing it existed. Instead, he simply says, suppose by way of contradiction that such a program P exists. That's a program P that solves the halting problem. Then we can modify P to produce a new program P prime that does the following. Given another program Q as input, P prime... Okay, wait. So wait. Alright, so let me just, like... Okay. P prime runs forever if Q halts. So wait, can we just open up the fuck is going on? Okay, so why can't I even write anything? There we go. Alright, suppose P of A, suppose there exists P that takes a program A and decides if it halts. Then we can modify P to P prime. What gibberish is it fucking on about? So then... Oh, we can close this. So then... So wait, so that means that... So wait, so P of A is true if A halts. Okay, so then if P of A... Right, something like this. If Q halts... then run forever. Otherwise, halt. Wait. Yeah. So you don't really need this. Does that work actually? Okay. Yeah, so that's what I meant. Oh, wow. So then the next thing is you do p prime of p prime. So if p prime halts, then it will run forever. Now we probably should start at this. Semantic truth and syntactic provability in first. The completeness theorem applies to any first order theory. If T is such a theory and phi is a sentence in the same language. One sometimes says this is anything true in all models is provable. I don't even know what that means. Yeah, see, this is the thing that keeps confusing me. Okay, first off, okay, let's just read it. In the last chapter, we talked about the rules for first-order logic. There's an amazing result called Gödel's completeness theorem. I don't know how to fucking say it. I'm gonna say Gödel. Y'all Germans or whatever, come after me. It says that these rules are all you need. In other words, if starting from some set of axioms, you can't derive a contradiction using these rules, then the axioms must have a model. They must be consistent. Okay. Should we say logic? So isn't that just like the same thing? In other words, if starting from some axioms you can't derive a contradiction, then the axioms must have a model. Alright, let's just ask. A set of axioms is called consistent if you cannot derive a contradiction. A set of axioms has a model if there exists an interpretation in which all the axioms... I don't even know what that means. What's the simplest set of axiom? I'm guessing it's going to be just like A and not A, but like, what is A? Right, but like, what is P? But that makes sense. Oh. What is it called? Constructive. What is it called? There's an. Oh, CSG. Yeah. No, all of that stuff. All these freaking acronyms that I've keep seeing. See, that's what's so annoying. You go to something like this and there's like no mathematical definition of it. Yeah. Okay. This is not what I'm doing right now. Oh yeah, I know what I'm doing right now. We'll just keep going. So how do you prove the consistency? You can't prove your own consistency, right? Think about what that means. It means that Fermat's last theorem or the Poincare conjecture or any other mathematical achievement you care to name can be proved by starting from the axioms for set theory and then applying these piddling little rules over and over again. How does Gödel prove the completeness theorem? The proof has been described as extracting semantics from syntax. We simply cook up objects to order as the axioms request them, and if we ever run into an inconsistency, then that can only be because there was an inconsistency in the original axioms. One immediate consequence of the completeness theorem is the Löwenheim-Skolem theorem. Every consistent set of axioms has a model of at most countable cardinality. So if we were to look at like piano, is that really what that says? Löwenheim is a theorem on the existence and cardinality of models. So what's the definition of a model? I actually don't care. Oh, jeez. I hate when they do this, bro. I actually love this stuff, dude. It's so cool. That a set of first order sentences has a model. So wait. Okay, yeah. Wait, hold on. This is what I want to... See, that's so annoying. They call it a structure. Is it a structure or a model? Why do you guys got so many different names for this thing, man? What? So what is it? Okay, dude, whoa, I'm getting overwhelmed. Is there examples? Didn't really help me, actually. Alright, what is it? Every consistent set of axioms has a model. Why did I say yes, that's the idea? I said, what does this mean? If the language, the set of symbols and formulas you're using is countable. If the language is countable. So, okay, so like, wait, but hold on. If the language is countable, what the fuck? This is kind of a shot in the dark. But the string itself is countably infinite, right? Oh, God. What does that mean, bro? At most countable cardinality. When you say that a model has a countable cardinality, what does that actually mean? Every consistent set of axiom has a model of. That means that there could be a model with uncountable cardinality. But there's also one. It's kind of a crazy proof. How does that work, man? The incompleteness theorem says that given any... Yo, what's up? Yeah. All right, it's crazy. I took a class on this and I still never fully got it. The incompleteness theorem says that given any consistent computable set of axioms... Okay, so first off, how do you prove that a set of axioms is consistent? Because that's where this thing gets nutty, bro. How do you prove that a set of axioms is consistent? Oh, dude, I'm just going in circles, bro. Blood is goofy, ah. Blood is so goofy, ah. Blood, you're so goofy, ah. Oh, blood, you're so goofy, ah. So, this is what's so weird to me. The incompleteness theorem says that given any consistent computable set of axioms, there's a true statement about the integers. So, like, why? What does the integers have to do with any of this? That can never be proved from the axioms. I didn't get that. Okay, so what is the completeness theorem? The completeness theorem says, not that I fully understand this, but if you have a consistent set of axioms, then there exists, okay, I'll say the word, but who the heck knows what it means? There exists a model that has, at most, countably many no. That's Lowenheim's golem. What is the cardinality of a model? It means how many sentences there are, or what? So if the model is like first order logic, yeah, I feel like querying the cardinality of a model means asking how many elements are in the domain of the structure that satisfies a given set of axioms. It's weird that the axioms are... In model theory, a model is a structure consisting of a domain along with interpretations of the symbols. This is surprising, dude. If this means what I'm like starting to understand, then that's very surprising. Is it? What does yield do? I don't even know what yield does. Okay, wait. So what is the completeness theorem? Bro, I was trying to read this. This thing makes no sense, bro. Okay, wait, hold on. Okay. A deduction is just a computable thing? Oh my god, dude. A first order formula is called logically valid if it is true in every structure for the language of the formula. I.e., for any assignment of the values a deductive system is called complete if every logically valid formula is a conclusion of some formal deduction. The deductive system is called complete if every logically valid... The problem is I don't understand logically valid. I hardly understand deductive system. I'm so dumb, bro. What's an axiom? An axiom, I believe, is just like a I mean, I would say a statement that you assume to be true. Okay, wait, hold on. In the context of first is a fundamental result that bridges the gap between semantics and syntax. I keep seeing this and I don't understand it. In other words, no matter how you interpret the dude, I need more examples, bro. I don't get it. Like predicates or functions, the formulas always come out true. A formula is syntactically provable if there's a finite sequence of logical steps of proof deriving that formula from a set of axioms using the inference rules of the logical system. The completeness theorem states a formula is semantically valid if and only if it is syntactically provable in the deduction system of first order logic. The soundness theorem tells us if you can prove something, it must be true in every model. All right, let me read the whole thing, but what I want is an example of this whole thing about models. A formula is semantically valid if it holds true in every possible model. In other words, no matter how you interpret the non-logical symbols, like predicates or functions, the formula always comes out true. The completeness theorem is the converse. If a statement is true in every model, then there exists a formal proof of it. Bro. Yeah, I wanna be gone with the incompleteness theorem for now and just be like, what the. Like, why do I feel so stupid? A model is a structure that gives meaning to the symbols in our language. A domain bro. Way to assign meanings to not. Alright, I gotta go though, I think. Okay, I gotta go.